Good afternoon, and welcome to today's Electronic Design Webcast. Our topic today, Silicon Carbide Solutions for Energy Infrastructure Market, sponsored by ON Semiconductor. I'm Bill Wong, Senior Content Director with Endeavor's Design Engineering Group. To begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. The webinar interface allows you to resize the presentation by clicking on the maximize icon or by dragging the lower right corner to enlarge the window. Additionally, we welcome your questions during today's event. We'll answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your questions into the question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. Now let's meet today's speaker. Stephen Shackle is a Business Development Manager at ON Semiconductor's Power Solutions Group, responsible for industrial marketing. He has spent all 9 years of his semiconductor industry experience, including roles in product engineering, applications, and marketing with ON Semiconductor's Power Solution Group. You can learn more about our speaker by clicking on the blue Speaker Bio widget on your console toolbar. Now let me turn things over to our presenter. Stephen, the floor is yours.
Thank you very much, Bill. As mentioned, I'll be covering silicon carbide solutions for the energy infrastructure market. So a review of the brief review of the agenda, as we'll look over, give an overview of the energy infrastructure market, specifically in solar inverters and EV charging stations. Then we'll dive into some of the silicon carbide advantages that play into the energy infrastructure market. Followed by a comparison of modules versus discrete solutions, and then when to use silicon carbide and power modules inside of energy infrastructure. And then we'll spend some time exploring the different implementations of a high voltage auxiliary power supply in terms of power semiconductors, and then followed by the solutions that ON has to offer in this space, and additionally a review of gate drivers, silicon carbide gate drivers that are needed to power the silicon carbide MOSFETs. So first I wanted to just touch on how our power grid is evolving as alternative energy is becoming more of a significant part of it. And it's becoming more of a significant part due to the cost effectiveness of it and its increasing cost effectiveness. So if you do a comparison between coal, it may range between $60 and $143 per megawatt hour. If you look at how much a solar utility scale implementation is per megawatt hour, it's around $36 to $44. So significantly starting to become cheaper than conventional energy generation. But one of the areas of concern is during peak demand is when solar, during the main afternoon and early evening times, is when solar starts to drop off in terms of energy generation. So the utilities and the market is starting to gravitate to implementing energy storage to store that energy that is generated during the day for use at a later time. So we'll dig into how that old grid is structured today. Looking here, you can see it's more of a top-down approach. The utility providers are generating the power, and that's flowing downstream to the consumers in all industries, commercial, residential, and industrial. This allows utilities to really adjust the supply to meet the demand, and is also maybe not the most clean way of generating power. So, as mentioned before, the grid is evolving. And that is now turned into a grid that looks like this versus you see the addition of solar, wind, and utility storage. But the other main area that changes is you see the arrows are not necessarily a top-down approach, but it's more of a bidirectional power flow. So you have consumers that used to only consume the energy, now providing that energy onto the grid, either being stored by utility or being used by other areas of industry, which is causing a distributed grid structure. When you have a distributed grid structure and the utility may not have full control over that, it causes some uncertainty, instability, and reliability, which is ultimately what utilities are judged on. So it's a little bit of a concern, but ultimately this is the trend in the grid structure as people are migrating to implementing a distributed system. So this ultimately plays into where how power semiconductors are used in a grid implementation, energy infrastructure implementation, as there's more use cases for that, and the adoption of silicon carbide will be critical in the acceleration of a new type of grid structure. Looking more specifically at solar inverters, as this is a heavy application that uses silicon carbide and power semiconductors in general, you have different types of systems. You have a central system that normally combines all the different solar modules and then does the power conversion from that. This has typically been how solar utility scale implementations have been done in the past decade or so. One of the concerns here is if one of the solar modules fails, that causes a whole system failure. So downtime is never good and causes issues with reliability in the grid. So we see a trend to move more to string inverter systems that increase the reliability of the system and also can provide some increase in efficiency as there's less losses in some of these string inverters. And this is where we'll focus a lot of our conversation on, is in the string inverter systems today. Lastly, you do have microsystems. These can be microinverters or DC to DC optimizers that will feed into a string inverter. These are ultimately give the best efficiency because they can control the output power based on a panel level compared to a string or a central perspective. So highest efficiency can be generated from a microinverter, but you do have a more costly solution here as it involves more components. Digging into the block diagram of a string inverter, we'll focus here really on the power blocks, and those are the DC-DC boost block that will boost the voltage from the solar panels up to a high voltage DC rail. And then from there, it will feed into a DC to AC inverter, feeding that power onto the main lines. Additionally, there's a DC-DC auxiliary power supply that would be used to power the control system. And then really as you get into some of the residential areas, they may incorporate an energy storage system inside of the inverter itself. And this is where you'll have a DC-DC charger to charge the batteries. Looking at EV charging stations, really there's two different types of EV charging stations. There's the AC charging station, and which is mainly just doing a monitoring and passing that power onto the car itself, and the onboard charger of the vehicle is actually doing the power conversion. So not much interest for us there. Our key interest is in the level 3 or DC charging and DC fast charging, where power conversion is happening in the pole itself. Here, power density is going to be critical, and is where we see a lot of adoption of silicon carbide here, as you're trying to fit up to 350 kilowatts into a pole, and space is, of course, a priority, as you don't want these gigantic stations consuming a lot of space and intimidating users. So we do see silicon carbide devices being a key enabler of DC fast charging stations, which will ultimately drive the adoption of EV vehicles. As a huge limiting factor to that is the range anxiety that consumers feel. Again, turning to a block diagram of a DC fast charger. Similarly, there's 4 main power blocks that we'll be looking at today. You'll have a 3-phase rectifier PFC stage that will take rectify the input voltage, and that will feed into a DC-DC. Normally, we see this as a full bridge or a full bridge interleaved LLC type of topology, and then that will go into a secondary rectification, which will ultimately charge the batteries of the EV car. Again, the secondary rectification, low-cost solutions may just use a silicon diode and migrating to silicon carbide diodes, but ultimately, for the most efficient solution, that will be a silicon carbide synchronous rectification on the output. So now with the overview, now we'll change gears to what does silicon carbide provide in terms of advantages to these systems compared to traditional silicon power semiconductors. First is there are no reverse recovery or QOR characteristics in silicon carbide, are very little compared to a superjunction MOSFET or IGBT technology. For conduction losses, it's dramatically lower in terms of both low VF for a silicon carbide diode or the low RDS(on) of a MOSFET. There is a good current stability, leakage current stability throughout the varying temperature degree, which ultimately will pass on to strong reliability of silicon carbide devices. A high surge and avalanche capacity compared to silicon diodes. And then ultimately having a higher operating temperature of 175 degrees C at the junction, which is a key spec and a need in some of these high power applications that we see within energy infrastructure. And how this plays into the benefits of the overall system. Of course, with lower conduction losses and losses overall, the power density can be increased and lower the overall system costs as you're requiring smaller cooling elements such as heat sinks to deal with the heat loss that might be in a silicon solution is dramatically lower in a silicon carbide solution, so you get an overall cost savings there. Additionally, as you can switch a silicon carbide device at a higher frequency, this will reduce the EMI and create a simpler system to ultimately design. And then in terms of how ON plays into this, we are manufacturing only on 6-inch wafers, and we have the, I'll discuss that a little bit later on. We have a patented termination structure, and you'll see that from ON strategy, we are really focused on creating robust and reliable silicon carbide devices. We see this as a distinguishing factor in the market and to eliminate field failures, and that will further accelerate the adoption of silicon carbide. As that is a major concern is the robustness of silicon carbide. So that's where we put a lot of our emphasis on, and you can see that on some of the technology we have released. And then, of course, lower VF in our diodes, which result to a higher avalanche energy capability and UIS capability. If we turn gears and actually look deeper into how silicon carbide benefits a solar inverter, I'll first point your attention to the top right corner where we're looking at the efficiency improvement of a 5 kilowatt boost converter, comparing it using just silicon diodes compared to silicon carbide diodes. You can see a 73% reduction in the overall power loss of the system when you're using silicon carbide diodes compared to silicon. And this will ultimately result in a smaller size reduction as we move to the left-hand side of this slide, where we're comparing a 20 kilowatt IGBT solution to a 20 kilowatt silicon carbide solution. we're able to get a smaller size in the overall system simply by, we have lower power losses, which will ultimately result in a lower or smaller heat sinks that are needed in the system. Additionally, since we're able to operate at higher switching frequencies, the magnetics and or inductors and capacitors in the system can be sized down dramatically, resulting in what you can see is almost more than a 50% decrease in the size of the solution. What this means to actually in the field is you may only need one person to install a silicon carbide solution compared to needing 2 people to install a IGBT solution, which will simplify or reduce the installation costs, which will accelerate the adoption of the devices themselves. And then lastly, the conversation always comes up with in terms of the cost associated to using silicon carbide devices. So it is true, silicon carbide MOSFETs are more expensive, depending on what type of technology you're comparing it to. It is a significant increase. But what that enables you to do when you use silicon carbide is operate at higher switching frequencies, as I mentioned. And this will reduce in smaller inductors and capacitors. And using these smaller inductors and capacitors can reduce the overall BOM cost of the solution to make it to where it's either on par or sometimes cheaper than a traditional silicon solution. So yes, overall, silicon carbide MOSFETs are more expensive than IGBTs, but as a full system perspective, it is a comparable in terms of cost. Now, if we look at how modules play into the energy infrastructure market, and for clarification, PIM is resulting in means power integrated modules. The main, and I would say the largest benefit, is the ability to simplify the assembly process, which will ultimately save production time during manufacturing. This is done mainly from using one device compared to multiple devices that you would need in a discrete solution. And I'll touch a little bit more on this on the next slide. During the design of the system, since we are taking care of a lot of the mechanical from a module perspective, and we're co-packaging devices inside, the resources needed for layout and knowing how to disperse the heat of a discrete solution can be limited, so we can, which will require lower engineering resources. Additionally, the circuit inside of the module is guaranteed by us, and we've done a lot of optimization of the circuit inside. So if you look at perhaps a T-type NPC, neutral point clamp topology, we've done our due diligence to make sure we've optimized all the devices in there to get the highest performance in that type of topology. That's one of the benefits of using a module, is that engineering resources may not need to be done on the customer's side. And of course, as you're using less components, it does simplify the manufacturing supply chain, and then that also enables you to get to market faster, which will ultimately make the customer more competitive in the market. So as mentioned before, I would do a little bit more comparison on the assembly process of a discrete solution compared to a module solution. First, you can see is in terms of mounting this onto a heat sink with the screw count. Typically, our modules will only require 2 mounting screws, and say if you have 6 or 8 different discrete components in that module, those are 6 to 8 screws that you would need to mount, say, a 20247 package onto a heatsink. And then when you're doing this, you normally, for a discrete solution, will need some sort of isolation foil or material that goes between the heatsink and the package itself, the tab of the package, to create the isolation. That's an extra material needed there, where from a module perspective, we have isolated base plates or DBCs already you incorporated within the module itself. So we have taken care of that isolation barrier for you. And then lastly is when you are screwing the device onto the heatsink. In terms of modules, you can apply equal force throughout the module, creating a very good thermal contact between the module and the heatsink. And there is a risk in terms of discrete solutions that the package itself will sort of warp up as you're only applying the screw to the top of the package. You could have a bad thermal contact towards the bottom of the package. So there are some robustness or reliability concerns with that, because the device will ultimately start running a little bit heater, but you're not getting that strong thermal contact that you thought you might be getting. So ultimately, in summary, just from a module to a discrete solution, I went through a good amount of these. I'll touch just on the cost overall. From a device-to-device perspective, the discrete solution, of course, will have an advantage there. But when you consider the overall solution cost, again, modules start edging out of the discrete solution as it simplifies the assembly process, may reduce the amount of rework and scrap in the process as well. And then also it's just easier to manage as you're managing one component compared to multiple components inside of there. So now when to use silicon carbide and modules themselves, again, we'll take a deep look at solar inverter, looking at the two different main stages of a solar inverter, the boost stage and the output stage. First, looking at the boost stage, you can see silicon discrete, and I would say mainly IGBTs here, dominate the, I would say, 10 to 30 kilowatt range of the market. You start to see silicon carbide discrete becoming more popular in this, and we see this trend continuing. Use silicon carbide discrete devices in the low power range of a boost stage. But as you move to the higher power range of ranging from 80 to 136 kilowatts and even higher, the adoption of silicon carbide modules, including hybrid and full silicon carbide modules, start to becoming a major player here and dominating most of the new designs that we see occurring today. Then looking on the right-hand side, we have the output stage. Here, below 10 kilowatts, silicon IGBTs are the main device used. We hardly see any kind of silicon carbide discretes used in the output stage. And then as you get above 30 kilowatts, silicon IGBT modules start dominating this space. And the reason why we see IGBTs being used more here is just the fact that it's operating at slower switching frequencies, and you may not be getting all the benefit you could see in silicon carbide, since it's a lower operating frequency as compared to a boost stage implementation. But we do see silicon carbide making it into some new designs, and we see this trend increasing as cost and as they move into higher power levels. Silicon carbide usage is increasing. The next view is a very similar story. It's just a different way for us to view this, more putting an end use case on it. So if we look at residential below 10 kilowatts, the boost stage is mainly using superjunction MOSFETs, where ON has an offering of devices, and then for the output stage, discrete IGBTs. As you move into residential between 10 kilowatts and 30 kilowatts, the boost stage becomes more of a silicon carbide solution, and then using a T-type NPC type of module using IGBTs for the output stage. And then above that, really the trend is starting to use more and more silicon carbide for both the commercial and utility scale types of implementations. Now, I know I mentioned this a little bit before, but I want just to show the schematics here and the evolution for the boost stage transition to silicon carbide. I would say probably 5 years ago or so or more, it was almost nearly all designs were using an IGBT and silicon diode implementation for the boost converter. And then starting a few years back, it moved into more of a hybrid solution. And that hybrid solution is where we pair a IGBT with a silicon carbide diode. And then ultimately, more and more new designs are coming to a full silicon carbide solution where we have the silicon carbide MOSFET paired with the silicon carbide diode. Then in terms of the output stage, again, we commonly see a T-type neutral point clamp topology being implemented here. Different ways you can sort of do this circuit, and we see a transition happening more and more hybrids where they're replacing the diodes again with silicon carbide diodes to increase the performance. And additionally, ON has a portfolio that ranges between the Q0 pack, the Q1 pack, and the Q2 pack as you increase the power capabilities going from left to right. The Q2 pack has a base plate on the backside for increased power capabilities. And then, as mentioned, for sort of the residential market, we do have three-phase all-in-one modules in a Q1 pack where we incorporate all three output phases into one module compared to using one module per phase. Then looking at some of the blocks in terms of an EV charging station or even just in general for energy infrastructure, you might have an active rectification stage or a PFC stage. Specifically for EV charging stations, we see a Vienna rectifier implementation being very common, so we do have solutions and modules for that. In terms of trends and when to use silicon carbide devices, mainly if your main design decision is low cost, of course, silicon diodes and IGBTs are always going to be the solution there. For silicon carbide diode, or for high performance, we see the pairing of silicon carbide diodes and superjunction MOSFETs. And in both of these instances, ON has an array of products offered here. And then on the right-hand side, if the highest performance is needed, and additionally, if you need bidirectional capabilities, this is becoming a trend within EV charging stations, using a six-pack implementation of MOSFETs is a solution that we see being adopted in the market, and we have modules that will be capable of supporting this need. And then lastly, the last block that we will look into is just your general DC-DC and output stages. Normally, as I mentioned before, in an EV charging station, this will just be a full bridge or full bridge interleaved LLC type of implementation. Typically, this solution is using superjunction MOSFETs, but similar to the previous slide, if higher performance is needed, using silicon carbide diodes with IGBTs is a preferred solution. And this is where we have actually developed some devices that have what we call discrete hybrids, to where the co-packaged diode with IGBTs is actually a silicon carbide diode rather than a silicon diode. And then lastly, similar to before, if you need the highest performance, using full silicon carbide MOSFET, whether that's in a half bridge, full bridge, or a six-pack configuration, is a solution there. So now I'll turn over to a view of high voltage auxiliary power supplies, as these are critical elements within the solution itself. This doesn't necessarily tie directly to energy infrastructure, as there's a lot of other markets that would be requiring high voltage auxiliary power supplies. This is whenever you have a high voltage DC bus that you need to power your control circuitry or fans from, you need some sort of high voltage auxiliary power supply here. So I'll first dig into different ways you can implement this. And I'll only be focusing on the power switches themselves. There's a lot of conversations that you can have on different topologies or different control ways of doing it, but I'll focus more on the power side. So first, and there's a common way of implementing this, is just to use a high voltage IGBT or high voltage MOSFET capable of up to 1700 volts. You do get the high blocking voltage from here, and it's very easy to drive, but one of the large contributor factors of why you wouldn't want to use this is the high conduction and switching losses in a solution like this. And it also can only be switched at a lot lower frequency. Next is if you use two silicon MOSFETs in series with each other. Again, you get the high blocking voltage that's required for the application. But when you're putting two devices in series, of course, you'll have a lot higher RDS on, which will increase the system losses. Again, it operates at a lower switching frequency, and since you are driving two different devices, it is a more complicated drive circuitry compared to just driving one device. Thirdly, is a solution of from a paper from Fairchild Semiconductor, which is now part of ON, is using a ESBC or emitter switched bipolar cascode solution, where you're putting a BJT in series with a low voltage MOSFET. This is a good way to get a high efficiency out of the system. We demonstrate a 300 volt DC bus. You can get 84% efficiency. Since again you are driving two different devices, it's a little bit more of a complicated drive circuitry, and it is limited to around 75 kilohertz of switching frequency. So lastly, which is why we're here talking today, is how silicon carbide plays into this. In terms of advantages, again, it's a single device that gets you that high blocking voltage. As discussed before, it is a low RDS on option, and then it can operate at higher frequencies, and since it is a single device, it is easy to drive, even though there are some drive considerations that you need to take into consideration, which we'll touch on the last bit of this presentation today. So just looking at some numbers here, and the size comparison between an ESBC implementation and a silicon carbide solution. First, the EBC is running around 75 kilohertz compared to silicon carbide that we can run up to 300 kilohertz. What this higher switching frequency results into is about half the size of the PCB, a much lower build height, and of course able to handle 20% higher power, even though the PCB size is half. If we look at just the efficiency curves of these two different solutions, comparing a 300 volt DC bus compared to a 600 volt DC bus, you see at the 300 volt bus, a silicon carbide implementation is about 3% higher. If you move to a 600 volt, that decreases a little bit to about half of 1.5% higher, but still a significant increase in efficiency. So silicon carbide really allows us to have smaller size power supplies using less components, and then ultimately providing a higher efficiency. So in terms of what ON has to offer in this realm, we do have a wide portfolio of MOSFETs ranging from low voltage to high voltage MOSFETs, including super junction MOSFETs, a wide range of IGBTs, and silicon carbide MOSFETs along with diodes. And then we are in the midst of developing gallium nitride devices. If you look at it from a packaging perspective, we have a wide range of discrete packaging, from your legacy style packages of TO247, TO220 style packages to more new DFN style packages, say like a SO8 5x6 package. And then also where thermal performance is crucial, we do have dual cool options to where exposed pad on top of the package is present to increase the thermal performance of the device. Transfer motor modules, these are more for motor control applications, but we do have some intelligent power modules, or IPMs, that have a PFC topology inside of them. And then lastly, we've already discussed the gel-filled modules that we have. In terms of our wide bandgap strategy at ON Semiconductor, specifically silicon carbide, there's public agreements that we have supply from some substrate and epi suppliers, but it is our long-term strategy and public strategy to manufacture our own substrates, as we want to be a completely vertically integrated silicon carbide supplier, as we do with a large portion of our business. From a fab perspective, we already manufacture our silicon carbide devices in-house, and our fabs have the tooling ready to migrate to 200 millimeter devices once the technology itself is capable of doing that. In terms of packaging, we do all of our packaging in-house and have a full portfolio of diodes and MOSFETs, and also die and wafer cells available, and also array of modules. And then we are offering deep application and know-how, system know-how for automotive and industrial applications with a global support team. If we look at our portfolio of modules, I mentioned our Q0, Q1, and Q2 style packages, but we also have our F1 and F2 style packages. All of these are mass market style packages that are have multiple sources. We have options for the pins, whether you need press fit or solder pins, and also whether you need a thermal interface material, or TIM, or without TIM. If you look at the overall portfolio that we have for silicon carbide, we have 650, 1200 volt, and 1700 volt silicon carbide diodes released today in a variety of different packages, as you can see here. In terms of MOSFETs, our 1200 volt series and our 900 volt series of MOSFETs are released on the market today in a TO247 3-lead, 4-lead, and the 2-pack 7-lead packages. Our 650 volt MOSFETs will be released later this year, and then we have development ongoing for 1700 volt devices. In terms of modules, a full array of hybrid and full SiC modules. The hybrid you'll see mainly in the diode space, and then full SiC will be when we're incorporating the MOSFETs inside of here. And then lastly, I will touch on silicon carbide gate drivers. Silicon carbide devices themselves are quite different in terms of how you want to drive them compared to superjunction devices. First is the VGS threshold of silicon carbide MOSFETs are normally lower than a typical high voltage MOSFET. What this means is to ensure that the device is off, you want to ensure that the gate driver can supply a negative voltage during the off stage to ensure that the device is fully off and stays off during the time you want. In terms of capacitances, they're comparable to superjunction, so the need for a gate driver to have high peak current turn on and turn off is needed. And then lastly, for silicon carbide devices, the larger the gate voltage you apply to the gate, higher, the lower the RDS(ON) will be. There is some trade-off between short circuit withstand times as you drive, but in some applications it is desired to have a high gate drive on the silicon carbide MOSFET. So having a gate drive that is capable of supplying up to 25 volts is critical, as some applications may demand that. So this is where we have our NCP 51705 silicon carbide gate driver that builds in and has all these features that I've mentioned, in addition to having DSAT and overcurrent protection. It has that internal negative VE charge pump, so you don't need to have a complicated circuitry outside to get that negative voltage. Programmable UVLO, or under voltage lockout spec, and then is also in a very compact 4mm by 4mm EFN style package that can be placed very close to the silicon carbide MOSFET, as you want to eliminate the parasitics and the traces to increase performance. And then lastly, as that device is not isolated, there is some need to have isolated drivers, and we have isolated IGBT gate drivers. What we have found and what we have tested is that this NCD 57000 series of devices can be used to safely drive silicon carbide as well. It does have DSAT, it does have Miller clamp, some other features that are needed to drive silicon carbide. So this is a solution that can be adopted where you need isolation. So with that, I want to say thank you very much, and then we will open it up to the Q&A session.
Excellent. Well, a few of you have already submitted questions. We're going to jump right in. If you'd like to submit a question, type your question into the question window on the side of your screen and hit the submit button. While we're answering your questions, please complete the feedback form, which is located at the bottom of your screen. So, for the first question, what about low voltage output? For example, a 48 volt or 80 volt battery. Is silicon carbide appropriate for the low voltage side of this?
So, generally, no. Silicon carbide, what we see in terms of performance is really going below 650 volt, an application requiring 650 volt devices. Silicon carbide just doesn't have the performance benefit compared to cost trade-off. So for low voltage applications, silicon carbide is not the preferred method or preferred choice. In terms of new technology, I would point to gallium nitride, as we see a need for gallium nitride in the 100, 150 volt space. So I would point you to looking at gallium nitride for a low voltage applications if you're looking for the next generation silicon or semiconductor technology.
Okay. Do you have power cycle specifications for the modules?
Yeah, so all of our modules do go through power cycling testing, and we have some data that we can share with customers that we are engaged with. But in general, power cycling is comparable to what is out in the market today.
Okay. Is there a trend in using silicon carbide modules versus discrete silicon carbide transistors?
So yes, the trend is to start using silicon carbide modules compared to discrete. As we see, this is most of the activity that we see in designs is migrating to using modules compared to discrete solutions.
Okay, slide 12, you talked about suppliers. Does ON Semi buy the silicon carbide substrates or produce their own?
So yes, as of now, we are procuring the substrates, as you saw from the agreements that we have from multiple sources, but we do have our strategy, and we are in development of doing that internally ourselves. We do have some capabilities in terms of splicing the substrates and boules. So today we are acquiring those and procuring those externally, but in the future we will be able to supply those internally ourselves.
Okay. Are there any advantages to using silicon carbide at lower switching frequencies?
Yes, so there is applications such as motor control where you would use have a slower or lower switching frequency, and the main advantage for doing that is for the conduction losses and reducing the overall size of the heat sinks. So, for example, if you need to put a motor, the drive of the motor on top of the motor itself, you could see some benefits in using silicon carbide there. So we see, but generally speaking, higher switching frequencies are dominating the adoption today.
Okay. Is EMI greater when using silicon carbide or with silicon transistors?
So in general, you'll see that as you can switch a lot faster and you can have some control, that we see EMI being improved using silicon carbide over silicon devices.
Is there a particular package you recommend for discrete silicon carbide FETs?
Yeah, so when deciding when to use discrete MOSFETs, it's recommended to use either anything that can give you access to the Kelvin pin or an additional source pin of the device. So if you're comparing a TO247 3-lead to a TO247 4-lead, the preference would be for you to select that 4-lead as you can improve the performance of the devices and get actually a better signal back to the gate.
Okay. Will GaN devices eventually be superior to silicon carbide?
Again, that depends on the application that you're looking at. Anything below 600, I would say at 650 volt and below, GaN, of course, will become, I believe, be more superior than silicon carbide. But GaN will never be the choice in applications that may require 1200 volt or 1700 volt. Silicon carbide will dominate that space. So it's a in-between answer there, but it really just depends on the application itself.
All right, but how does GaN fit within the energy infrastructure?
So a similar answer, right? That really depends. Go back to one of the previous questions with the 48 volt batteries. It could fit within that space, but anything usually in energy infrastructure, we need voltages above 650 volts. So it's going to be very limited access or very limited usage of GaN in that system, energy infrastructure systems.
What's the lowest RDSON you have for silicon carbide FET modules?
So as of today, it depends on really the topology, but we do have 6 milliohm devices in a half-bridge configuration in our F2 package, but we do plan to have a wide portfolio of modules ranging up to 80 milliohms with in between 10, 20, 40, and 60 milliohm ranges in a variety of different packages and configurations.
Well, we need to wrap up at this point. If you asked a question that was not answered, we'll be in contact with you soon to answer all your questions. This concludes today's presentation. On behalf of Electronic Design, I'd like to thank ON Semiconductor for sponsoring today's event, and of course to all of you for joining us. Have a great rest of the day.